Does the universe remember information? We often say that information disappears. Old memories fade, sound scatters into the air, light that once seemed so clear vanishes into darkness. Something similar happens in the quantum world. A quantum state may hold several possibilities together, but when it meets its surrounding environment, the delicate relationship between those possibilities begins to dissolve. We call this decoherence. But does information truly disappear completely? Or does it change into a form that we cannot yet read, leaving a trace somewhere in the universe? Several recent studies in physics appear to deal with completely different subjects. One calculates how quickly gravity can disturb a quantum state. Another investigates the geometric trace left behind after a quantum state travels around a closed path. Some researchers have placed several qubits of information inside a single photon. Others are examining phase shifts in superconductors and the tiny distortions in the shapes of distant galaxies. At first glance, these studies seem far removed from one another. Yet a common question lies at their center. Does nature remember the path it has traveled? Today we will follow this question through quantum physics and gravity, through superconductors and the cosmos, and connect them as parts of one long journey. Let us begin with gravity. Gravity is both the most familiar and one of the strangest forces we know. It pulls an apple toward the ground and keeps the planets in orbit around the sun. Yet our attempt to describe gravity completely in the language of quantum theory remains unfinished. So can gravity also destroy quantum coherence? A recent study carefully calculated the decoherence that appears when matter interacts with quantized gravitational waves. The important point is that gravity does not simply push or pull an object in one direction. A gravitational wave stretches and compresses space itself. It acts on the overall shape and mass distribution of an object. It is less like pushing a small pendulum with your finger, and more like twisting, ever so slightly, the entire room from which the pendulum hangs. This kind of coupling produces rules that differ from those of ordinary environmental noise. Instead of a process in which a single vibration is exchanged at a time, two vibrations may become involved together. Different selection rules may also appear depending on whether a quantum state has even or odd parity. Some forms of coherence can disappear easily, while others may be protected in surprising ways. But the calculation also delivers a sober conclusion. Under realistic conditions, decoherence caused by gravitons is extremely small. This is why a tiny anomaly in an experiment cannot immediately be declared a signature of quantum gravity. Thermal vibration, electromagnetic noise, mechanical instability, and measurement error can all produce much larger effects. This result also sets an important standard for information gauge theory. Suppose there is a field associated with information itself, and suppose it produces a form of decoherence that differs from ordinary gravitational effects. It would not be enough to say that coherence simply disappears a little faster. The theory would need to predict which states decay more readily, how the effect scales with mass and distance, and which rules remain unchanged when temperature and environmental conditions are varied. New physics may be hiding in a place where established theory predicts only a tiny effect. But that same place is also where countless forms of noise can hide. Science therefore asks for a baseline that can be measured and compared before it accepts a mysterious possibility. Now let us enter the space in which quantum states move. When we think of a journey, we imagine visible places such as a mountain trail or a route across the sea. But a quantum state travels not only through the physical space around us, it also travels through a space of possible states. If we slowly change an external magnetic field, the intensity of a laser, or the energy structure of an atom, a quantum state traces a path through this state space. The interesting part begins when the state completes a closed path and returns to where it started. Its starting point and ending point may be the same, yet its phase or orientation may have changed. Imagine walking all the way around a mountain and returning to the same location, only to discover that the compass in your hand now points in a subtly different direction. The change that remains after a journey around a closed path is called holonomy. A recent study placed projectors, rather than arbitrary descriptions of individual quantum states, at the center of the analysis. When several quantum states overlap and share the same energy, the decision to call one state the first and another the second may depend on an arbitrary choice. If that choice enters the calculation, it becomes difficult to distinguish a genuine physical effect from a difference in representation. Projectors allow us to remove this unnecessary freedom and observe how the entire space formed by those states moves. This method connects the quantum metric, Berry curvature, topological invariance, and Wilson loops within a common language. In other words, it can record not only where a quantum state was, but also which route it followed before returning, without allowing the answer to depend on an arbitrary choice of basis. This is especially important when studying information holonomy. If information holonomy is a real physical quantity, it cannot change merely because an observer uses different coordinates or assigns different names to the states. After standard dynamics, Berry phase and instrumental drift have been removed from the measured phase, a residual effect must remain and repeat in the same way. Holonomy is the memory of a path that remains after the journey has ended. A person may return to the same home from which the journey began, but not return as exactly the same person. The location is unchanged, yet the direction of the mind has shifted. The geometry of quantum states may also carry the history of a journey that cannot be reconstructed by looking only at its beginning and its end. Can this memory of a path be tested in a real device? In a recent photonics experiment, researchers encoded several qubits of information into multiple degrees of freedom carried by a single photon. Ordinarily, creating a large entangled quantum state requires many photons to be generated and made to interact at precisely the right place and time. But as the number of photons increases, the probability of producing the desired state falls, while loss and mismatch become more serious. The researchers distributed several pieces of logical information within one photon and used a programmable optical circuit to create graph states and cluster states. Instead of asking many travelers to walk along separate routes, they gave one traveler several maps and sent that traveler through a complex network of paths. Such a high-dimensional single photon could become an intriguing tool for testing information holonomy. It allows us to compare several paths inside the same photon, rather than struggle with tiny differences between separate photons. We could construct routes that should produce the same logical result, but follow different physical orders, and then connect those routes into closed loops. Would reversing the direction of the route reverse the sign of the residual effect? Would enlarging the loop increase the signal, according to a definite rule? Would the signal disappear along an open path and remain only when the path is closed? Without predictions like these in advance, a measured difference would be more likely to reflect an instrumental error than information holonomy. Another optical experiment observed quantum non-classicality in a causal network made of 3 nodes. 2 independent sources of entangled photons transmitted information, while a deliberate intervention was performed at the central node. The researchers analysed not only what they observed, but also how the data changed before and after the intervention. They found correlations that were difficult to explain using a classical causal model. This result is not evidence for information gauge theory. It is a non-classical phenomenon understood within standard quantum mechanics. Even so, the experiment offers a method for distinguishing the causal routes through which information has travelled. If an additional information phase were to accumulate around a cyclic causal path, a network of this kind might one day become a laboratory in which to search for its trace. Now let us move from optical circuits to superconducting loops. Place a very thin barrier between 2 superconductors, and pairs of electrons can cross a barrier that would be difficult to pass classically. The phase difference between the 2 superconductors is then transformed into an electrical current. This is the Josephson effect, because an invisible quantity called phase appears as a measurable signal in current and voltage. A Josephson junction is an extraordinarily sensitive instrument for searching for new phase effects. But a sensitive instrument is sensitive not only to new physics, it is also sensitive to familiar physics. A recent study showed that spin-orbit coupling, a ferromagnetic exchange field, and higher harmonic currents can work together to produce an intrinsic phase shift, even without an external magnetic field. A Josephson diode effect can also appear, in which the current flowing in one direction differs from the current flowing in the opposite direction. This result is an important warning for experiments designed to search for an information gauge phase, offset induced by a temperature gradient. A measured phase shift must be separated from conventional effects produced by spin-orbit coupling and magnetization inside the material. Imagine hearing unfamiliar footsteps in a dark room. Before claiming that they reveal the presence of something unknown, we must check whether the sound came from vibrating pipes, a contracting building, or wind passing through a narrow window. The search for new physics must proceed in the same way. The temperature gradient must be reversed. The direction of magnetization, the magnetic field, and the orientation of the junction must each be inverted. The different harmonic components in the relationship between current and phase must also be analysed together. If an information gauge effect exists, it should display a reversal rule or a temperature dependence that differs from known phase shifts. What makes a new theory strong is not only the number of phenomena it can explain. Sometimes what matters even more is how honestly it can exclude false signals that resemble its own prediction. Now let us widen our view to the scale of the entire universe. The universe records its history of growth in the distribution of galaxies. Gravity from matter in the foreground bends the light arriving from galaxies far behind it by a tiny amount. By statistically combining the shapes of enormous numbers of galaxies, we can infer the distribution of invisible matter and the rate at which cosmic structure has grown. This is weak gravitational lensing. A recent cosmic shear study combined the conventional method with a clipping technique that reduces part of the influence from extremely dense regions. High-density regions contain a great deal of information, but they are also strongly affected by baryonic feedback and complicated nonlinear processes. It is like dimming the brightest part of an image so that structures hidden in the darker background can be seen more clearly. When the two statistical methods were combined, the constraints on cosmic matter density, structure growth, and the properties of dark energy improved. From the perspective of information gauge cosmology, this method is particularly interesting. Suppose an information field changes the growth rate of galaxies while leaving almost unchanged the relationship between the two gravitational potentials that bend light. In that case, a distinctive difference might appear between conventional lensing statistics and clipped statistics. But in cosmology, matching a single observation is never enough. A theory must describe the expansion of the background universe, the growth rate of galaxies, redshift space distortions, and weak gravitational lensing at the same time. If a different parameter is selected for every observation, the theory may be able to explain anything, but it will predict nothing. Gravitational waves offer another way to distinguish between theories. Recent research has explored how a new dynamical field could change the effective friction experienced by gravitational waves as they travel across the universe. This means that the cosmic distance measured with light might differ slightly from the distance measured with gravitational waves. Information gauge theory must therefore answer a clear question. Does the information field affect only scalar perturbations that help form galaxies? Or does it also alter the propagation of tensor perturbations, such as gravitational waves? Whichever answer the theory chooses, it must produce an observable difference. The strength of a theory does not come from leaving every possibility open. It comes from being able to say that some possibilities will not occur. Finally, let us turn to Wilson loops. Why are quarks never found alone? In quantum chromodynamics, the force between quarks does not simply fade away as they are separated. When we try to pull them apart, the vacuum stores energy like an extending string. Eventually, that energy creates a new pair of particles. This phenomenon is called confinement. One of the most important tools for studying confinement is the Wilson loop. We imagine a particle traveling around a closed path through a gauge field and calculate the total phase accumulated along that path. If the effect of the loop decreases according to the area enclosed by the path, rather than merely its perimeter, an area law associated with confinement appears. A recent study considered the loss of ordering information that occurs when several insertion points on a path coincide in supersymmetric Yang-Mills theory. It proposed a way to calculate loop equations while preserving the order of those insertions. This approach may also be relevant to attempts to define composite Wilson loops containing insertions of an information current. But caution is essential. This result does not mean that the mass gap problem of pure Yang-Mills theory has been solved. It provides one proposed element of an area law in a supersymmetric theory, while stability and the full fluctuation spectrum still require further investigation. In science, a beautiful mathematical structure and a completed physical proof are not the same thing. So what do all these studies tell us about information gauge theory? First, a new form of information decoherence must possess an operator structure and selection rules that differ from standard gravitational decoherence. Second, information holonomy must be a gauge-invariant quantity that does not depend on the names assigned to states or on a choice of coordinates. Third, the theory must predict in advance a signal unique to a closed path, as well as how that signal changes when the direction of the path is reversed. Fourth, the coupling strengths and mass scales used in photons, ions, hydrogen atoms, Josephson junctions, and cosmology must be related to one another. Only when these conditions are satisfied can an information holonomy residual become a testable physical quantity rather than an unexplained experimental error. Imagine taking the phase measured around a closed path and removing every known contribution. We remove standard dynamics, Berry phase, electromagnetic effects, thermal drift, and environmental decoherence. If a residual still remains and follows the same reproducible rule, then it becomes scientifically interesting. But that residual cannot be explained arbitrarily, after the experiment is over. Its direction, approximate magnitude, and dependence on experimental conditions must be predicted before the measurement is made. The papers we have explored today do not prove information gauge theory. What they do is show us where a signal might be sought, which background effects must be removed, and which mathematical language may be needed to define the result. For a new theory, this is encouraging news. It is also a demanding examination. Human beings store memories in the brain. Nature does not use the word memory. Instead, it leaves its history in correlations and phases, in curvature and symmetry, and in the rules that determine which transitions are allowed. When we return home after a long journey, the location of the house may not have changed, but our thoughts and the way we see the world are no longer exactly the same. If we compare only the beginning and the end, it may seem that nothing happened. Yet the path remains within us. Perhaps quantum states are like that as well. Perhaps superconducting currents, the distribution of galaxies, gravitational waves and loops drawn through the vacuum cannot completely conceal the histories they have travelled. The work of a scientist is not to believe in those traces before they are found. It is to remove every other possible cause and then ask whether the same trace remains. New physics begins with a residual that cannot yet be explained, but only a residual that is repeatable, falsifiable, and predicted in advance can survive as a new law of nature. If you found this journey fascinating, please subscribe and give the video a like. Together, we will continue following the invisible traces of information toward the deeper questions of the universe. From ThothSaem's Science Catch,